Am I all set? Sorry for that. So, so my name is spelled differently, both on the proceedings, on my tag, on everything. So I think it's just much simpler if I just change my name for this talk. So I've just removed the H from my name. Interestingly, that spelling mistake is something that is cross-cultural, cross-gender, cross-everything. So I think the mistake is more of my dad's than my birth certificate. But anyway, this is Self-Improving Algorithms. It's with joint work with Nir Eiland, Bernard Chazelle, Ken Clarkson, Ding Lu, and Wolfgang Meltzer. It's actually on a sort of series of papers. I'll be mainly talking about the first one, and I'll tell you about some of the others. So let's start. So initially, I started with this slide explaining, what's the problem with worst case, but then I realized that, this picture actually explains this slide much more better. Does anyone get this? It's preaching to the choir, exactly. So there's no need for that slide. So what we'll instead start with is a story. So there was an evil banker who wanted to steal all of our money, and but to do that, what he had to do was he had to actually sort the values of the stock market. So you had basically various prices coming in, and on Monday, so he uses a sorter, and he gets something. And again on Tuesday, he gets another set of values. He uses a sorter again, and he gets some other answer. And this goes on. Day by day, this keeps happening. And on Friday again, he gets some value. But then he realizes, that n log n time is just too much. For these people, milliseconds or microseconds or nanoseconds are important. So, but what the banker realizes is maybe stock A5 seems to always beat stock A2. So if you're really paying attention to the slides, you would have actually noticed that A5 is always above A2, but you don't have to. So he could basically design a sorter where this comparison is deferred to the end, because in some sense it's not as important. So in some sense the idea is, algorithmic tasks are often repeated over and over again. So in that sense, some expected running time makes a lot of sense for such tasks. And related to that, it's the ensemble of inputs themselves may have some useful structure that you can use. So for example, maybe after looking at the distribution from which these inputs are coming, you realize that, well, this stock is always better than this. So you don't have to actually make that comparison in the beginning. Essentially that leads to, the distributional view, which is instead of thinking of an algorithm just having some input, you think of there being a distribution D, which is generating inputs. And this algorithm is given some input x from D and has to compute f of x. Now, we'll assume that this is actually a distribution, this is a fixed distribution, and the algorithm is processing independently sampled inputs. You might think of, maybe you want some sort of Markov distribution or something, but for the sake of this talk and in all of our results, we actually think that there's some fixed distribution which is independently generating inputs. So it makes sense you look at the expected running time over this distribution, and in which case the worst case behavior is sort of averaged out. This is sort of standard sort of average case analysis, which is usually what you do is you say this distribution is uniform. Or you have some really nice description of what this distribution is. And that's the biggest problem that we all have. Interestingly enough, after talking to physicists, for them, when they think of an arbitrary input, they actually just think of a uniform distribution. It's so to some extent, I think this is part of our dogma that sort of a uniform distribution is bad. But still, I agree that this is not something that's desirable. And in reality, in quotes, whatever that means. But if you were to say have some sort of a if you were to assume that your inputs were coming from a distribution, you don't want to assume that it has some nice structure. Sort of real life distributions may not even be expressible. They may be extremely complicated, but there still may be some structure within that you can exploit. So even though you can't describe the distribution, you may be able to learn something from it. And so of course the ideal would be if you had an algorithm that would work for all distributions, but we sort of don't expect that to happen. But sort of self-improving algorithms is sort of some step towards this extremely big ideal. What it tries to do is it tries to be optimal for a broad class of distributions. So I'll explain that in more detail. But essentially, it's an algorithm that initially has a worst case guarantee. So if you were sorting numbers, initially it's just quicksort. And it starts learning about the input distribution, starts learning some structure of the distribution, and then tries to become faster based on that knowledge. So the idea is, if the data was coming from, say, a low entropy distribution, then the algorithm should run faster. That's sort of the overall, that's sort of the basic intuition. And the next is, even though you have an input distribution, which may be impossible to learn completely, you may still have some structure worth exploiting that you can actually pick out. So just to give you a sort of pictorial view of that, so suppose, here you've got your distribution, there you have your algorithm in its most primitive form. That's like a picture of ENIAC or something like that. But what you get is, so first you get this input x1, and then of course this thing goes ahead and computes f of x1. And as you can see, it took a long time for that arrow to appear. That was deliberately chosen. So anyway, so this goes on for a while for k rounds, and again, it's sort of slowly computing whatever it has to do. But after k rounds, it's learned something about the distribution, and it stores that information in some data structure that it builds. And after that, it basically becomes a much faster algorithm, like this. And now you'll see that it actually computes things actually quite quickly. So the idea is basically it's learned enough about the distribution to optimize itself for this distribution. And this goes on. So essentially, D, the distribution, is initially unknown, but it's fixed. It's not changing over time. We have samples that are independently generated from D. There's a training phase of k rounds. So this is like the inputs x1 to xk, where the only guarantee you get is a worst case guarantee. And then the data structure starts storing information about this. And the limiting running time, which is what you get after the training phase, here the running time is an expectation over the distribution. This is better than worst case, sort of whenever possible. And more importantly, it's specifically optimized for this distribution. So I'll quantify what this means for our specific result. So what we do, at least the first result, was a self-improving sorter. So you have a sort. So x, the input, is a list of n numbers. And so what does it mean to be optimal for this distribution? Well, x is a random variable. So pi of x, which is basically the output of the sorting algorithm, which we'll think of as a permutation, is also a random variable. This is a discrete random variable because let's think of n as just being, it's always, you get n numbers to sort. So if you look at this entropy, which is, pi of x is this discrete random variable. Look at the entropy of pi of x. This is a lower bound for any comparison-based sorter, or indeed for any sorter that gets one bit of information for every single operation that it performs. So we'll call a sorter to be optimal for the distribution D, if it takes O of that entropy plus n, of course, because this quantity could even be much less than n. So for certain distributions, the n log n worst case can be beaten. And of course, this gives a very nice expression which says what does it mean to be optimal for a distribution. So if you want an example where this quantity is small, so here's an interesting, suppose you have n numbers. The first number is chosen uniformly at random from between one of two numbers. The second number is chosen uniformly at random between one of two other numbers, so on and so forth. You can count that the total number of permutations that can be generated is just 2 to the n. So the entropy will just be log of that at most, and it will be linear. So for distributions of that form, we would like to sort in linear time. And that's what a self-improving algorithm will try to do. So, and specifically, we will be looking at product type distributions. These are distributions where, so the input x is the sequence of numbers x1 to xn. So x1 is independently chosen from d1, x2 is independently chosen from d2, so on and so forth. So we're specifically focusing on product distributions, and in a slide I'll tell you why we have to make that. So essentially each component of the input is independent. There is no assumption made on what the distribution di is. It could be completely arbitrary, and we want the sorter to be optimal for the distribution d, where d is of this form, where optimal is basically you have to match that entropy bound. So the first result was a self-improving sorter for product distributions. So D is initially unknown. There's a training phase of n to the epsilon rounds, where epsilon is some parameter that you can choose. And after n to the epsilon rounds, it basically builds a data structure of, it's not O of n, it's like n to the 1 plus epsilon, but it's near linear size. And after that, the running time is optimal. It's actually O of h of pi of x plus n. So this is really interesting because regardless of the distribution, as long as it's of product form, so the distribution may not even have a simple representation, it's still able to match exactly the information theory bound here. And so any questions about what the result actually is?
How long does the training phase take?
It takes n to the epsilon rounds, and in each it basically it has to spend n log n just to sort the input. So it's basically n to the 1 plus epsilon log n.
So you're running time, not number of comparisons.
This is running time, not number of comparisons. Although it's all in the comparison model.
Are you optimal time of comparison?
Yes, because it matches this the entropy bound. Plus n, right? So there's that additional n that's you have to read the input. So I guess that's so.
Those aren't comparisons.
Sorry?
Those aren't comparisons.
Those aren't comparisons, right? So yeah. Any other questions? Okay, and you might ask why this restriction of product distributions. Before I go there, here's another sort of pictorial view of what's going on. Again, the first k rounds, that's n to the epsilon rounds. You're spending n log n time, and after that, you actually will sort optimally in expectation. And the reason you need some restriction on the distributions is that if you had a self-improving sorter that worked for all distributions, then you would require exponential storage. So this is essentially some sort of, it's not a very complicated counting argument, but it's important to have that so that we can justify, that we have to make some restriction on the class of distributions that our self-improving sorter will work for. So in this case, we made this product-wise restriction. Yeah?
So what do you mean by storage? Is that, the number of training rounds need to be gone?
No, it's so if you assume that after the training rounds, it basically has to now become a fixed comparison tree. So it needs to basically store some information from the training phase, and then based on that sort. So that data structure has to actually have exponential number of bits in it. Essentially because there are just too many distributions out there that if you had low storage, you couldn't sort all of them optimally. Yes?
So what is the product distribution? Can that product distribution produce every permutation?
You could take the uniform distribution. You could say that, the uniform distribution can also be generated through a product distribution. So am I answering your question, or?
Maybe. So how do you do uniform distribution?
You could just say that, let the first number be anything between 1 and n. The second number is also uniformly between 1 and n, so on and so forth. So all the distributions are basically the same.
So IID samples will generate a uniform distribution.
IID sample, exactly, yeah. Exactly. IID sample, where each of those is IID will generate that.
If you take a random permutation, and that's your distribution, that's one, but it's random, but there's only one. That's any permutation. So you need n log n at the beginning, but then it's constant. There's only one, so it's output the same.
Okay, now you confused me again.
So they're two different things, which is why it's totally different from self-adjusting things, because they're two different concepts. So take one random permutation and make your distribution being just this. The support is just one. So once you've done the n log n work, then in linear time, you can just, next time there's a question, it's going to be the same permutation anyway. So you just have these.
You just spit out your canned answer.
Exactly, yeah.
So it's a cache, really.
Yeah. Yeah?
You said the supplemental data structure has size n to the 1 plus epsilon.
Right.
So does that mean that the training rounds actually run slower than n log n, or does it only access part of the data structure at any point?
The training rounds, it will still just be no. It won't be slower than n log n. I think you could probably distribute all the work over your training rounds. I think you could because you have n to the epsilon training rounds, and you're building a data structure of size n to the 1 plus epsilon. You could basically ensure that all of your rounds actually spend at most n log n.
And then also, what happens if you hand the algorithm something that's not a product distribution? Does it sort of fail gracefully and just revert back to a naive sort?
It's really hard to say because it could probably fail miserably. Yeah. I mean, if you did something, if you did something where essentially there was only one distribution, like yeah, if you correlated things will go haywire basically. Right. So I'll just explain, how the self-improving sorter works. So the key insight is basically for product distributions, there happens to be a single typical instance. So in some sense, there's some instance which really represents what the distribution looks like. And I'll explain what this means. And this is what you determine in the training phase. And most other inputs, this statement is really false, but in essence, it's kind of true. Most other inputs are close enough to this training instance. I mean, again, it's false, but I'll explain why that's sort of true in essence. And essentially, because you've already sorted the typical input, you can quickly sort the new input, which is, in the case that Bernard was describing, if you only had, suppose your distribution was basically one fixed permutation with a little bit of random noise, made to each of them, then essentially you just need to know the sorted order of that fixed permutation, and then everything else will just follow. You can do it quickly. So in the training phase, how do we compute this sort of typical instance? Well, take the first log n input, so x1, x2, up to x log n. And so of course, when you get x1, you sort x1. When you get x2, you sort x2. But then, by the way, sorry, this is a little misleading. It's capital X1. So x1 is actually an input, and x2 it's an input of n things. And you've got k of them, where k is log n. So what you do is just sort all of these at the end. So now you get this long list, sorted list of k times n numbers. And now you just pick every kth element. So you pick the log n, the 2 log n, the 3 log n, so on and so forth. That gives you a list of n elements, which we'll call the v list. So the thing is that this somehow is a typical instance. And the reason for that is it's more convenient to think of this list as actually binning the real line. So this is the real line. That's the number v1, v2, v3, so on and so forth. Now what you could do is now just perform this random experiment where you just sample x1 and you see which bin it falls into. So it falls into the bin v3, v4. You can sample x2, it falls into some bin, so on and so forth. And essentially, it's not hard to prove the lemma that the expected number of little xi's that fall into your bin is O of 1. So which means if you chose a random input and you said how many numbers of this random input are going to fall into some bin, that is O of 1. So in some sense, if you can figure out which bin each of your input numbers is in, that's almost sorting. It's fairly close to it. I mean, of course, there are large variances and deviations, but you can take care of it. And essentially, it says the structure of a random input from D, from your distribution, is reasonably well represented by your V list. So this is what it means for your V to be typical. And so now, it's not too hard to, I can actually describe the algorithm completely. So let's again, do this sort of thought experiment. Take the number xi and let capital Zi be a random variable, which is the bin that xi falls into. So, in other words, if you were to sample a random xi, it might fall into this bin. You sample again, it fell into this bin, so on and so forth. This is some random variable which has an entropy hi. Right? So the entropy of capital Zi is hi. Now, just for the sake of, for the thought experiment, assume that you actually knew the distribution di. Well, if you knew the distribution di, you could come up with this thing called a di tree, which is the optimal search tree for xi. So, usually if you wanted to search for xi in this list, you just do binary search. But if you knew the distribution, then you could actually do a sort of the proper search for that distribution, which means instead of splitting at vn over 2, you would split at the point where the probabilities are half on both sides. So that is what I'm going to call the di tree. If you knew the distribution, you could construct this. And even if you didn't, if you got enough samples from the distribution, you could get this to a reasonably good accuracy. So now the way the algorithm works is you've got the v list. Now you get this x, which is a list, x1 to xn, these numbers, and you want to sort them. So take, by the way, the animations that you're going to see here are just going to blow you away. I'm serious. So you have the D1 tree, and you just search for x1 in this tree, and it falls into some bin. And now you could basically take the D2 tree, you look at x2, and you search for it, and this falls into some bin. So just leave it in that bin. And you keep doing this for all the numbers, and x1 to xn, these numbers are basically in these bins. Ooh. So, and then the only thing that's left to do is basically internally sort each bin, in which this is even better. So you just internally sort the numbers within each of these. This took ages. But now if you looked at what is the total time that the algorithm spent, you had to search for each xi. So it's a summation over I of the search plus the time to internally sort within each of these bins. So, and this, on expectation. So on expectation, each search takes h of I. This is because we constructed that optimal search tree. And the expected number of xi's that fall into each bin is big O of 1. So the internal sort actually takes O of n. I mean, you can make this argument formal. So, so essentially, your time was the summation of these entropies plus n. This is what you pay on expectation. Of course, the thing is that what we actually promised was that the running time should be h of pi of x plus n, and it's not even clear why these two should be related. So this is where sort of a very interesting information theory argument comes in. The initial proof was actually much more complicated, but later on when we were trying to extend this to other regimes, we sort of found this really clean and cute way of arguing this. Note that h of pi of x is an extremely unwieldy thing to argue about, because even though x is of a product type, the max of x itself is a highly dependent thing. It could be highly correlated. Like if you wanted, what is the the kth element? This is extremely hard to argue about. But you have this simple lemma that says, suppose capital Y is some random variable, and capital Z is some function of Y. So capital Z is also a random variable. And if you can compute Z given Y using t comparisons, then actually the entropy of Z is less than the entropy of Y plus t. Why? Because to represent Z, you just represent Y, and then you give all the comparisons that the algorithm makes. So when you have an algorithm to go from one random variable to the other, you can also make some argument about the entropy. This is fairly simple to show. So now consider the random variable capital Zi, which I described, that's the bin that xi falls into, that a random xi falls into, and just put them together as this sort of product type thing. So capital Z is Z1, Z2 up to Zn. So capital Z is also a random variable now. Now, you can argue that given pi of x, you can compute capital Z in linear time. And that's just through a merge. So if you're given pi of x, it means you're given the sorted order of all the little x's. You can just merge that with v1 to vn in linear time, and you can find the bins that each of these falls into. So in linear time, given pi of x, you can find all of these zi's. So basically what that lemma says is that the entropy of capital Z is the optimal entropy plus O of n. And then of course these guys are all independent. That's where the independence of the distributions comes in. So you say the summation of hi is actually equal to hz, and that's bounded by the entropy plus O of n. So this is how the argument is made. I mean it's kind of slick, but this idea is really useful. And essentially what you do in the training phase is you can construct the v-list. I showed you how to do that. You can get the DI trees fairly easily. You just need enough samples to construct a tree. And you basically get, I haven't gone into why the space is n to the 1 plus epsilon, because it looks like the space is n squared, where you spend n for each tree. But you can do a couple of time-space trade-off tricks to get rid of that. And so that's basically the self-improving sorter. I'll just spend like the last few minutes just saying, there have been places where we've been able to extend this in computational geometry to do more complicated things. For example, suppose you wanted to compute the Voronoi diagram of n independently distributed points. So the Voronoi diagram is basically sort of the nearest neighbor partition of all of space. So each vertex point is associated with a cell which contains all the nearest neighbors. So with Ken Clarkson, we had a self-improving algorithm to compute the Voronoi diagram, sort of along the same lines. And Wolfgang Molzer gave a much improved presentation of our result. And this is sort of has general interest from computational geometry perspective. So, and also, I mean, specifically we focus on the Delaunay triangulation, which sort of connects two neighboring input points. So I'm not going to get into details of what we did, but essentially, again, you have distributions d1 to dn. The point xi is now independently distributed according to di, and we have an optimal self-improving algorithm that follows the same sort of structure. The entropy now has to be defined appropriately for triangulations, but that can be done. And again, it's optimal for any product type distribution. And interestingly, the whole algorithm is basically, you just take the sorting algorithm, and every 3-line argument now becomes a page, because you have to bring in a lot of computational geometry hammers. But the basic idea is you can define your notion of a typical instance. This requires some epsilon net construction for disks. And then now, so now you need to have some sort of 2-dimensional search, and you can have some, there are things known to do that. And essentially, even though the computational geometry is fairly involved, the basic idea is still the same. And this was pushed a little further for maxima and convex hulls. Here it's actually very interesting because there are no typical instances, and the algorithms are god-awful. But you basically you can still do something. And in general, I mean, solving instances, these computational geometry instances on distributions of independent points usually has some independent interest. I mean, people look at these in various ways. So finally, to summarize, I initially had this slide which basically, this is your usual template summary slide, like, oh, this is what I did, that was great. No, what we did was really great. But instead, what I'll do is something else. So this, maybe to segue into the panel. This is me being nice to the model, and that's me being mean to the model. So I'm playing the devil's advocate with myself, because I've actually had this internal dialogue. So, the model is actually nice. It's clean because it gets away from the problems of worst case and average case. But you have to impose these restrictions on the distributions. Of course, there's no way of getting around this because of the lower bounds. But still, that's a problem. The other thing is that it's really nice that you get this very strong optimality for distributions. I think this is really great. And that actually gives some insight into the original problem at various times. But it's extremely hard to actually prove results. And the best we've been able to do with this model is shave off a log n factor. And this isn't all that great then. So there's no surprise that we resort to n log n problems that have worst case n log n, because we use these comparison tree models and optimality and entropy and all those things. So I had this discussion with Tim at some point. He thought that was okay, but I wish that there was some other problem where we could push this.
It's not your fault we don't have lower bounds on running times for almost any problems.
Right. But the fact that this model really uses explicit lower bounds in that form, if we could somehow get around that, then we could say more interesting things. And the model is sort of flexible. That's what I'd like to believe, but the results have been proven for this very fixed setting. But anyway, oops. Whatever. That was actually the last slide, and there was a pop-up that was supposed to come that was saying you can choose your side. But I'll end with that. Yes? No. I think the kind of improvements that. So interestingly, when I gave the talk about the Delaunay triangulation, someone had suggested that it might be implementable. But the improvements that we're getting are you're shaving off this log n factor. And there is a constant that comes about because of a time-space trade-off. So it's unclear whether that's actually worth the effort over there. Yeah?
Unrelated question, if that answered your question. So I was just wondering, how you might apply this to hard problems like SET. And I think one avenue was suggested in Kevin's talk, where maybe you don't want to use a lower bound on time because you don't have it, but maybe you can compare yourself against a bunch of heuristics. And somehow, I think one way to think of his work is to say that's some kind of self-improving algorithm. I was wondering if you had thought along these lines to sort of have a learning stage where you learn how to select from a bunch of heuristics.
That's actually an interesting point. In some sense, I've actually not thought of it from that perspective, but you can think of the sorting algorithm as, in some sense, implicitly selecting from a bunch of comparison trees. So it uses the information that it gets to select the right comparison tree. So it does have that sort of flavor. So actually, I think that's an interesting way of looking at things. We haven't done that. Yeah.
Have you any thoughts to allowing some kind of correlations between the different XIs, like somewhere in between, any independent distributions and full correlation?
So, I mean, even if you have like k-wise independence for, I think even reasonably large k, the lower bound still holds. Because even if you said, okay, let's like 100-wise independent, there are still sort of way too many distributions that are 100-wise independent. When you make them completely independent, then you reduce the space of distribution small enough for this to work. So I think one might have to instead even say something further, that maybe almost everything is independent except for a few things which are correlated. That's the kind of argument we'd have to make.
One thing I'll just add quickly, I mean, we looked at optimization problems and we're not very successful, but the intuition there, I think, maybe doesn't work, but at least it's very simple, and which is that you'd like to use the past, your training, to get a starting point. So there's our service, and if you know where to start, then you can really make progress very quickly. So the hope would be that things are not terribly different than at some point where to start. So we got some results, but they're kind of true. I mean, true in the sense that basically you start from the same starting point and always do better. So there needs to be something.
I mean, especially for graph distribution, somehow we were never able to get a nice enough result. I mean, here you have this like really clean result for sorting. So for graph results, you'd say, well, okay, then it ends up being like some GNP model or something. So it ends up going into a completely different regime. Yeah, it's that's why I put the we've only been able to sort of attack n log n problems. With maybe that's because of the way we're thinking about it, which is wrong.
Yeah, I guess following up on the comment from before, I see a connection between this and what we've done with algorithm portfolios. So the way we think of it is we're given a set of algorithms which are themselves black boxes and somewhat uncorrelated, and then given a fixed amount of training data, we learn how to discriminate between them. It seems like you're treating the set of algorithms as being kind of implicit.
Yeah.
And that might be one thing that's putting you in this kind of n log n land. You might imagine instead having kind of a given set of algorithms that you want to learn and discriminate on, and that might allow you to think about very well.
Yeah, I mean, yeah, I think the problem is if you start looking for optimality too hard, then you just end up at n log n then. Yeah.
So there's some kind of expert learning interpretation of this result, right? You're saying there are n to the epsilon or 2 to the n to the epsilon algorithms, and in the initial phase you learn which of these 2 to the n to the epsilon algorithm does well on the distribution, and
so it should be 2 to the n to the 1 plus epsilon, right? Because the space is n to the 1 plus epsilon. So, yeah, I know, right.
I mean, I guess I said 2 to the n to the epsilon because normally the
you think in each range you reach, yeah, exactly.
Yeah. So there are results where you do this exploration kind of stuff in the matrix space. And is it conceivable that some of those results say something about your setting?
It's I guess so. The problem, it's a little hard to interpret the information that we're learning as somehow. I mean, I guess implicitly you are saying that as soon as you learn something, you're getting rid of some comparison trees. You're saying, well, these comparison trees are bad, and yeah, it would require us to interpret the results interpret the algorithm in a different way. But I think it's probably a useful way of getting out of n log n. That's sort of my goal.
Just to follow up on Voronoi question about optimization. So there are some analogs in the optimization world where you have these allocation algorithms. You process the initial sequence heavily using some MP, you can find a small set of duals. You can be a data structure and use that small set for very quick allocation.
I see. Yeah. That's an interesting point. Yeah.
questions?